Welcome to our webinar today, everyone. I'll get going in just less than a minute. All right, let's get started here. Welcome to Ozen Engineering's webinar. Today the topic is RFID simulation with ANSYS Electronics Desktop. Our presenter will be Stephen Anchong Liu. Prior to him beginning, I will give you a quick introduction to Ozen Engineering. Ozen Engineering is a simulation-based company. We use finite element analysis, computational fluid dynamics to solve multidisciplinary engineering problems, and we work also with high frequency and low frequency electromagnetics. I'm proud to tell you that we are an elite channel partner certified by ANSYS, and most recently selected as the ANSYS Channel Partner of the Year for the Americas. As a channel partner, that means that we sell ANSYS software in Northern California. We conduct training sessions at our office or on-site for customers. We provide technical support to our customers, and we offer engineering consulting services for simulation projects. We work with the full suite of ANSYS tools, and we offer cloud compute services. We host a webinar either once a week or every other week. You can see previous topics listed to the right here. These are all available. You can view the webinar recording on our website under Webinar Library on the top link that's found under Resources. You can see here our upcoming schedule. 2 weeks from now, we'll be doing DC power design, then topics related to motor sizing, electrostatic discharge, motor noise, 5G, and digital twin. You can register for these upcoming seminars on our website under training, and if you want to subscribe to our newsletter, we send out a newsletter once a month with information about upcoming webinars, technical tips, and training sessions. ANSYS has made a lot of progress recently and now offers the ANSYS Cloud service that's compatible with applications mechanical, FLUENT, and the electronics suite. So the benefits of working with cloud is one-click burst to the cloud. You can solve large or compute-intensive problems that you don't have sufficient resources. You can prepare the models at your machine, and the task of submitting them to the cloud is integrated within ANSYS softwares, and the solvers are updated and the IT aspects are managed by ANSYS. If you're interested in a 30-day trial of the ANSYS Cloud, please contact us and we can set you up with that. This is our contact information. You can email us info@ozeninc.com, call us direct, and you can speak with an engineer or an account manager. While I have your attention, I'll say that we're currently looking for a mechanical engineer and electrical engineers, and particularly for somebody who has an emphasis in control systems for digital twin type applications. Today's presenter is Anchong Stephen Liu. He has received his bachelor's degree in electrical engineering from UC Santa Barbara. For our customers, they will know him as he provides technical support for electronics products like Maxwell, HFSS, and SI Wave, and Simplor. So with that, I'm going to turn over the presentation to Stephen.
Great. Thanks, Chris, for the introduction. I will turn to my screen. Okay. Today's topic is the full system RFID simulation methodology in ANSYS Electronic Desktop. So first of all, what is a full system RFID methodology? So in order to conclude that, it's a state-of-the-art simulation method that firstly utilize the best-in-class tools, which is our ANSYS tools, mainly HFSS. That's also a methodology incorporates actual RFID transponder, tag geometries, and transceiver receiver circuits. Uses the real-world signaling schemes and takes into account the entire operating environment, seamlessly combines frequency and time domain results. So in order to do a full system RFID simulation, what are the tools that's needed? So for the transponder and tag modeling, we will need ANSYS HFSS. For the full 3D environment simulation, we'll need HFSS as well. Real-world transponder and tag circuitry, and a realistic transmit received backscatter signals, we'll use the Designer tool. Nowadays, it's called it's an add-on option to the HFSS that's called SI option. And the methodology enablers will be HPC, meaning that for some large scale cases, we'll need to use high performance computing licenses to enable parallel solving to reduce the simulation time. For HFSS, it's a premier 3D electromagnetic design tool that solves any arbitrary 3D structure. There are multiple solvers in the software. The flagship software is the full wave finite element method. That's FEM. It also has a transient finite element solver, as well as integral equation, aka IE solver, and also a physical optics solver. The applications that it handles are varies. There's a lot of applications that HFSS can handle, from antennas, waveguides, filters, all the way to address your EMI circumstances, wireless components. All these things listed here, but not limited to it. What is a designer? So now it was called Designer back a couple years back. Now it's being the license has been restructured. So it's called Designer SI option. That's an add-on to the HFSS. That seamlessly integrates ANSYS HF tools together for full system simulations. It solves time and frequency circuit and the systems and system. What it uses is a state space or a convolution methodology. It also has a time domain SPICE solver, harmonic balanced frequency domain solver, 2D 3D method of moment solver. Applications for this add-on would be time and frequency domain for circuit analysis, time and circuit domain system design, signal integrity, antenna arrays, RFID simulation. What is HPC? As I said before, this is a distributed memory parallel solver technique. It can also distribute mesh subdomains to network of processors, which can So by using HPC, it can significantly increase the simulation capacity with the reduced simulation time. It's highly scalable to large numbers of processors. Automatic generation of the domains by mesh partitioning is user-friendly and load balanced. As you can see, it can distribute on the diagram here. It illustrates that the HPC can distribute mesh subdomains to network processors and memories. So for an airplane mesh, that's a relatively electrically large problem that takes time to solve, takes time to mesh. So as you can see, by using HPC, you can distribute the mesh subdomains, mesh individual parts of the geometry on different machines. After introducing the tools that that's involved in this methodology, what are the steps for such a simulation? So typically, we'll use HFSS to design and optimize the transponder and the tag antennas. Then use the designer part to design and optimize transponder and the tag circuitry. We then create a 3D model of the full RFID system environment. Link all above models together in the designer circuit using this which is a circuit simulator. Then lastly, obtain the full system's performance, either results, data, or metrics. So for the transponder antenna design in HFSS, it's just a simple case to display here. It's gonna have an operating frequency at 920 megahertz, 50 ohm input impedance, circularly polarized, return loss of negative 15 dB or better. That's our end goal there. Gain of 6 dB or better, and with a cross polarization that's greater than 15 dB. So there's the full picture, the full model is on the left. The cross-sectional view of an antenna is on the right. So using HFSS, we can do a rapid antenna tuning using the adjoint derivatives functionality. This new capability is for sensitivity tuning and optimization that computes the derivatives of SYZ parameters with respect to project and design variables, which can eliminate the need to solve multiple variations with small differences in the numerical noise. So which, using that will be more efficient and more accurate. This tuning functionality also gives you the real-time tuning of the reports to explore effects of small design changes. What this means is that if you have a variation, say on the dimension of the antennas, you can tune the result plot by just playing with different scenarios of different variations. As you can see, the plot here, the different color represents a single entry, a single number for the variation on a dimension. So with the different design variables, the results, the antenna performance will vary. So after the antenna has been tuned to the desired optimal performance level, we can plot a return loss in S parameter. We can also plot a 2D radiation pattern as well as a 3D far field pattern. We can also plot the electric field, also a far field pattern, LH and RH circular polarization, stuff like that. So that's the capability. That's the 3D capability in HFSS. After the antenna has been tuned, we can then go to RFID tag antenna design in HFSS. Similarly, its operating frequency will also be 920 megahertz. The dimensions are displayed here. Top half of the tag cut away will give you the coils inside. Backscatter length is frequency at 250 kilohertz. Omnidirectional antenna pattern. So as such, also we want this to be dustproof and waterproof. As such, we can plot the input impedance. Return loss is at optimal. I believe that's 920 megahertz there. 3D antenna pattern with omnidirectional 3D polar 3D pattern, a 2D radiation pattern as well. Then we use the the circuit tool to make the designer transmit circuit. So we have the mixer, the RF power amplifier, circulator, and lastly the power divider. So all of these can be break down into so on the upper part of the diagram, that's a simplified circuitry, and we can implement the details down below. And as you can see, there's MOSFETs, BJTs, and voltage sources, resistors, capacitors. All these components are available in the component library in the designer tool. And then we can do a transient simulation. The transmit circuit results can be plotted out at different locations on the circuitry right after the port, right after the power amplifier, or right after the power divider, the phase shifter. Based on antenna far field pattern, the designer can push the output results to HFSS so that a realistic far field pattern can be created. So as you can see in the results, we can push the excitations and make that the source of the far field pattern. So as we can see, the far field pattern has changed based on this pushed excitation. So then the RFID tag circuit, we can also build the power generation and the management, AMD modulator, and the BS modulator. So for the power generation and management, there's going to be rectifier, limiter, DC voltage regulator. On the AMD modulator, there's going to be envelope detector and a simple comparator. And on the BS modulator, there's switch and capacitor with a logic gate. So then we will charge the pump circuit. The top schematic is for the charge pump, which is the rectifier circuit used in the design. It used diode connected MOSFETs as rectifiers. It is the most unique and probably most important part of the RFID tag front end because its efficiency is directly linked to the operational range of the tag. The goal of this optimization is to achieve maximum DC output voltage on a resistive load, which is used to model the power consumption by all the circuit on the tag. So we can do that. We can do that at a given input power level by varying the transistor size and or number of charge pump stages. Because the input impedance varies with the transistor size and number of charge pump stages, it is also necessary to vary or sweep the RF source impedance so that uh, complex conjugate matching is achieved for all design variations. So the figure on the top left corner shows the DC output voltage of a particular charge pump designed for 4 stages as the size of the transistor and the imaginary part of the source impedance is swept. The figure on the top right shows the same results in a rectangular plot. Um, the voltage limiter, which is a low dropout voltage regulator, the rising oscillator, and the POR circuits are shown in this schematic. So the figure on the bottom right corner shows the static behavior of the voltage limiter or slash regulator as the input voltage, which is swept from 0 to 3 volts. We can see the outputs from the limiter, which is the green part, and the voltage regulator, which is the red part, are limited to 1.25 volts as expected. The figure on the bottom left corner shows the spectrum of the output from ring oscillator. It has a nominal frequency of 4 megahertz. For the AM demodulator circuit, the schematic right there is for the AM modulator, is the general schematic for the AM modulator. For the purpose of this is for the signal coming from the reader. So the envelope detector there at the beginning of the circuit is basically just a rectifier with a relatively small time constant. It is then compared with an average output of the envelope signal to produce the digital output stream. So the figure on the top left is the result is one typical bit cycle, where red is for the envelope signal, green is for the average value, and blue is for the output. The curves on the top right are for a more realistic case. So then we have this backscattering modulator circuit. The schematic there is for the backscattering modulator. It's a block on the entire schematic, but in details, if you push down a circuit that's consisted of multiple MOSFETs, and there's a drain and a data in voltage there. The 4 transistors on the right form the 4 transistors in the schematic in the modulator form a buffer to drive a switch that turns the capacitor either on or off. In the plot, the green curves in the plot are for the RF signal, so which the magnitude is clearly modulated by the digital stream blue. So as you can see, as the step function goes between 0 and 1, the RF signal changes its magnitude accordingly. So lastly, we can take a look at the overall tag circuit response. It's ideal for the IF source. So on the left, this entire figure mainly shows the waveform of a typical tag inventory cycle according to RFID Global Generation 2 standard. So the sine curve is the RF input in the tag. The two top zigzag curves are the voltages on various stages of the charge pump. The brown curve is the clean 1.25 volt DC voltage. The black curve, which is a little bit hard to see, is the demodulated digital sequence. So as you can see, after the 200 microsecond mark, the reader starts to send out constant waves. But we can see the amplitude of the RF input on the tag goes up and down, which is a clear indication of backscattering modulation by the tag circuit. So that was pretty much for the detail of the simulation. So let's step back a little bit, take a look at the realistic environment of the HFSS model. So the 3D view is a box on a landing belt, I would say. So there's going to be a transponder antenna steel rod, reinforced concrete columns, aluminum roller. So that's an aluminum roller conveyor system. The cardboard is the cardboard shipping container, metal container inside the container, and there's gonna be a tag on exterior of the container. So there's the dimensions and the different views. So we can, based on the realistic, with this realistic environment of HFSS model, so we can essentially build this 3D view, what we see here in HFSS, and then implement this realistic environment as a block, and then implement that in the circuit to give a full system model, combining all the models together. So on the left we have the RF power amplifier we discussed, and there's the demodulator on the right, and AM modulator, and the tag circuitry. So after that, we can see the full system transceiver antenna patterns would look like this. The full system field results would look like this. The tag located on the front of the shipping container has a radiation pattern like this. The mean low points in the wrong direction. So the tag located on the top of the shipping container tells us that the mean low points into the proper direction. Then the tag signals and the transponder receiver input. We have the RF input on the left and the backscattering modulation. So if there's no tag interrogation zone, the pattern looks like this. If the tag is in the tag interrogation zone, we can see a spectrum like this. So with that being said, we can have a simulation with an even larger environments that has 24 tags, 4 reader antennas, 900 same frequency, operating frequency. 2 instead of just 1, we can have 2 warehouse base, 20 gigabytes of the RAM total, 1.8 gigabytes of RAM per node, 11 nodes, and with that we can simulate the entire thing within 4 hours solve time. The dimensions are as such. So in conclusion, using the combination of HFSS and Designer, aka SI option, it is aka RF option, it is easily possible to design, optimize, and predict the performance of an RFID system in its intended environment. So also, we can have multiple arbitrarily located and oriented tags included in the model as well. Larger environment, as we've shown, are possible, and random random noise sources can also be included in the full system model, which can be discussed in details. There was a hands up. Can you have the slides? I will. Sure thing. I can. If you, let me see. How do I do this? Email is fine. I will. But not in the slides form. Probably, I'll translate that into a PDF and send it out. Can you please send an email to this support@ozeninc.com. Oh, okay, you have the email. Okay, I'll take that. Okay, can I copy that? Okay. Yeah, definitely. It can. I'll share the slide with you. Any other questions? If I can see. You're welcome. The earlier question was about the videos, which I think is already addressed. Okay. Nadim has a question. Go ahead. Let me see. Okay. Any more? Let me see. How do you define a radiation box size for these applications? So, typically use, so if you have the 3D model in HFSS, just, let's see, let's take an example here. Say you have this model, what I would do is just use the open box, and then just create an air box using that button, and this will, well, actually, sorry, this is already, there was already an air box created before, I believe. So there was an air box created before. Let's see. So we delete this. So now let's say this is the model, the antenna you have, and then you just click on the air box there and then set the percentage offset. Usually 0 to 5% is fine. Then this will 0% will be like edge to edge, like it's right out. It's right. It's like wrapping the entire model with no gaps in between, with no gaps on the edges. So you can change that by changing the percentage, and then after that we just assign a radiation boundary conditions on that box. That's the way how we usually do. Is a 13.56 megahertz. I'm not sure. For if you want that to be 13.56 megahertz, you have to tune it. I don't think the radiation box has anything to do with the frequency, your optimal operating frequency. That's dependent on the excitations and your model design. If you like, you can send a email to support. We can, with their project, we can take a look at. We can take a look at it. Okay, I will send. Meanwhile, I will have to send the PDF to you. Okay. Any other questions? Okay, great. Yeah, if you have any other further questions, inquiries, feel free to send emails or just call us. Email either support at Ozen Inc. or info at Ozen Inc. will work. Again, we appreciate your attention and your business. Without any further questions, this will be the end of the webinar. Have a nice day.